my presentation is about batteries. So the easiest way I think to explain this is through a AP Chem free response question, which is also the homework that I just finished. So a battery has two sides, which in this case are aluminum and zinc. So basically what happens is this oxidation reaction is happening at the aluminum side, which oxidate aluminum atoms into aluminum 3 plus and 3 electrons. So the aluminum 3 plus goes into the solution and the electrons are going through this wire to the zinc side. And then it combines with zinc 2 plus and reduces it back to zinc atom. Obviously, the flow of electrons has already completed the upper part of the circuit, and the other spectator ions, which are nitrates and potassiums, are also moving through the cell bridge to form the lower part. Essentially, the tendency of aluminum atom to split apart is driving every charged particle to move in the entire circuit, and this driven force is what we called the voltage of the battery. So I'm going to switch to my presentation. An actual battery is just what we see in this chemical system being wrapped into a cylinder or a plate or a box. But no matter what shape it is, the basic components of the structure is always going to be the same. First of all, it definitely needs two terminals to connect to the external wires. But different from the laboratory beaker cell, these terminals are not pieces that directly react. They are connected to the inner electrodes which are usually metal or some metal oxides that carries the redox reaction. And then we need the electrolyte so that the charged particle can be transferred. In modern battery, the electrolyte has been designed into gel or solid form instead of solution to avoid leaking. Finally, the most expensive part, also the parts that the beaker itself doesn't have, is the separator. Since the anode and the cathode are so closely together in the battery, some porous material is needed between them to prevent short circuits, while at the same time allow the charged particle to go through. There's no standard classifications of battery. In terms of its function, it can be classified as the non-rechargeable primary cell and the rechargeable secondary cell. In a primary cell, the reaction stops when the entire anode had been oxidized. It cannot be reversed. In a secondary cell, reverse reaction is available when you apply a higher voltage in the opposite direction to the batteries, which carries the electrons from the cathode back to anode. Wet cell and dry cell. Wet cell has a liquid electrolyte just like the beaker cell does, and dry cell has no free fluid but moisture that ensures that the current can flow. There are thousands of different structures and combinations of material available to make a battery, but the four common structures are bobbin electrodes, spiral wound, flat plates, coin cell. Most commonly adopted reaction materials are zinc carbon, lithium ion, and silver oxide. Bobbin cell has an internal cylindrical anode, usually in form of a rod immersing in the electrolyte. The external cup that contains the electrolyte forms the cathode of the batteries. There's a carbon needle in the anode that collects the currents and connects to the positive terminal. The negative terminal is the cup itself. Bobbin cells store a large amount of electrolyte, which gives it a high energy storage capacity, but the electrode surfaces are very small, which means the reaction is slow and the power is limited. The spiral cell is literally wrapping two big electrodes into a sushi roll. It is designed in order to carry high current by lowering the internal resistance with the electrode's tremendous surface area. However, since the metal foils are so closely wrapped together, there is less room for the electrolytes, so the capacity of the cell is reduced. This construction is used extensively for secondary cells, since the reverse reaction happens faster with larger surface area. Flat plate is the easiest to understand because it's identical to the simple beaker cell with just multiple metal plates parallelly constructed and soaks into the solution. It's the kind of batteries that builds into the front of your car, and given the volume of both of its electrolytes and terminals, it can achieve high power and high capacity at the same time. Coin cell is used where smaller size is required. So everything is small inside a coin cell, especially the separator and electrolyte, which are squeezed in between two chunks of electrodes at the top and bottom of the coin. Therefore, it delivers very low power. Classifying with materials. Zinc carbon is probably the kind that you get from the store. It's also associated with Bobbin's cell structure, and zinc is obviously the anode, but the carbon here only refers to the current collector. The cathode reaction is actually manganese oxide being reduced to a kind of crystal called manganate. Lithium-ion cell is the kind of battery in your phone. It's usually rechargeable and it comes with a spiral wound structure, but in this case it's folded into a rectangular shape to accommodate the shape of your phone. The electrodes of this battery is always some lithium compound, typically lithium cobalt oxide. It could be other things because it's only using lithium plus as a charge carrier. But why they use lithium instead of other random ions? It makes sense because it's being used as a charge carrier similar to electrons, so it has to be small and travel fast. And think about lithium. It's the third lightest element after hydrogen and neon. At the same time, it's a very active metal eligible for redox reaction. This is why it becomes so important for expensive electronic device. Silver oxide is even better than lithium ion in some way, since it has high capacity, high power, and is more stable. Lithium is so active that it's flammable, but silver is almost completely safe. However, silver oxide is only used in tiny battery like this because silver is so expensive. From the reaction above, the electrolyte is potassium hydroxide and sodium hydroxide, and you can actually get silver metal from this battery after the reaction complete. So, in summary, there are thousands of ways to design battery. The materials of terminals and the structure to wrap them up are interchangeable. You can make zinc carbon into a tiny coin cell, or you can put a big chunk of silver into the engine of your car if you're rich. There's always a trade-off between cost and quantity, between power and capacity, volumes and surface area. It's all about how you want to use it and whether the combination works. But everything goes back to the simple chemical reaction in the beaker. So this is my presentation. If you have any question, I'd like to answer it. Thank you.